It is spring of 1993, and we are on the campus of the University of Southern California. We are heading toward Powell Hall of Engineering to pay a visit to the USC IEEE Micro Mouse design team. Here we are, 5th floor. Let's see if there currently anyone in the Micro Mouse lab. Room 520. Okay. Up front we have the great Grant Imahara, who is the team leader for this venture and the pulse of the Micro Mouse team. Behind him is the wonderful Wade Bick, who is the senior engineer for the project and currently looking at pictures for ideas to incorporate into the mouse. Over here we have John Mui, founder of Mui's Constant, and another committed team member in the development of the Micro Mouse.
Okay, here we have Mona.
Oh wait, no.
Mona's in charge of requisitions and she's taking care of us financially. And here's
I
Anna.
don't know. Looking over there.
Anna.
Go away.
Anna is also part of the office staff. Let's see if Dr. Cool's in today.
Who's yeah, cool.
Okay. There you go. This is Dr. Cool. He's the chairman of the department.
You're right.
Dr. Cool has supported us with lots of funding and the resources of the department are at our disposal.
But some of the resources, not all of the resources.
I see. So some of the resources.
So I wish you good luck in your project.
Thank you, Dr. Cool.
Looking here in the lab, a mattress is installed so that team members can rest up a bit before classes or continue work on the mouse.
Let's go. Come on, let's go program some software.
Hey man, you are that iced cappuccino over here, right?
Yeah, what?
I guess that's what I was saying.
Yeah, I better get a case of that. That's good stuff.
What are you doing right now, Wade?
What am I doing right now? I'm simulating one of my software routines, the motor test routine, and I'm just running it through the emulator and making sure it does what I wanted it to do. And so hopefully tomorrow morning I'll hook the mouse up to it, and we'll see if the commands that we're sending are the correct commands to make it move forward and backward and left turn and right turn.
Derek Schaefer here. He designed the laser range finding system.
That's right, laser range finding system.
And SKUFix, one of the basic routines.
Fundamental
Routines of the Micro Mouse project.
Still working on that SKUFix.
Yes, he's still working.
Hi, I'm Holly Chung. I'm in charge of the architecture and the transport mechanism of the mouse. Let's see, let me show you what this mouse made of. Okay, everything here is custom made in the machine shop here at USC, all except for the shaft encoders and the motor. The shaft encoders we're using are by HP, and the motors we're using are high precision motors, which are just made about $100 each. But we are fortunate that we are able to get those for free from Sean, who is a friend of one of the members here. We're using laser diodes for sensors, foam tires for high friction and shock absorbance, 2 bearings. So this is a wheelchair configuration. And let's see, the whole thing is made of aluminum. That's it.
Alright.
And here is Harry Hollander, another member of the awesome IEEE Mouse team, having a coffee break.
Coffee break, just to stay awake.
The Micro Mouse team. You tell me, what are you doing?
I'm finished.
See what you're doing.
I'm cleaning off my soldering iron. Isn't that exciting?
Flip your board around. Tell me what is it?
PC board. Oh. See? This is the microprocessor. This is the mock. These store the memory. These store the motor drivers. This is going to be the register for the lasers, various capacitors, headers, other passive elements, and I think it's forever kits.
For the record, those are the sockets where those elements were gonna be.
Oh yeah, yeah, I guess.
Hi, right now I'm assembling the battery packs for a mouse. We are using 1.5 volt batteries, going lined them up in 6 packs, and stick formation.
Hey.
We are going to carry 1400 milliamps hours, and the total voltage of our mouse will be 14 volts.
Logic probe and soldering.
And this one, yeah.
Yeah, well, okay, alright, you got it. Something like that. Now, right now I'm trying to create a new motor test routine so that we can divide the debugging down into smaller chunks this week. Well, I tried to take on a little too much in the first test routine. That.
Here are the traces for the PC board layout. They were done on using OrCAD. Here are some of the codes for the software. As you can see, it goes a long way. And this is not all of it. Wade is one of the prime players in this project. He designed most of the hardware and software for the mouse. Right now, he is working on the software coding. Don is also a major contributor to the electronic hardware. Currently, like Wade, he is typing up some codes.
Yeah, you continually. That's the input port on the motor control chip. But you always check. This is checking the status of the port. If it's busy, then poles for waves. Oh, you're making me tired. The camera points on all the ultraviolet radiation.
The wheel rotates in the counterclockwise direction as viewed from the encoder end of the motor. Channel A will lead channel B.
So this is motor. This is the code wheel. This is the encoder, right?
Well, not on our system, but because we
But
don't
I
hook
mean-
everything up to.
But I mean, okay.
We don't hook the encoder up to the motor.
Okay, but in their system, from their reference plane, so the encoder side is looking, the encoder end of the motor this way.
Yeah, so it's
Looking
looking
this
that
way.
way.
Grant and Derek are discussing how to set the conventions for the controlling of the motors. Not enough can be said about Grant. He is truly a leader. Not only did he contribute to the hardware and the overall design of the mouse, he kept the team working coherently together. Not only did he organize the team, he also obtained the facility, equipment, and material and finance needed to get the mouse project on the run.
So
Now I am testing the mechanical transport system of the mouse. As can be seen, the mouse can move. It is like a simulation run of how the mouse will travel through the maze. Right now I am controlling it with a remote control without any sensory feedback. I am driving it through the maze, which I am not doing a very good job on. Hopefully the mouse will be able to navigate itself better than what I am currently doing. I think that's enough.
Okay.
Okay, one of our goals when we started with the Micro Mouse project is to make a better mouse than this kit that they bought earlier. And some of the differences and things that we improved upon are, first of all, overall size, which you can see is quite a big difference. Secondly, we've got a lot better sensor array. We've got 6 sensors, two on the horizontal sides and one in the front and the back. Whereas Mappy only has a couple in the front and a couple on either side. None in the back, making him asymmetric. He has a dedicated front. He can't run bidirectionally.
Wait, no.
As far as the electronics go, Mappy uses a Z80 microprocessor, which is very limited
Does anyone tell
in
you
its
what
capabilities
it is?
compared to the 68AC11, which would go here on our mouse.
Oh, yeah.
It also has very, because it's such a limited processor, it has to add on a lot of other chips, such as these 8255 I/O ports. It also has non-integrated form motor drivers, whereas all of these chips here, these power, I guess they're power BJTs, along with their extra components, are replaced by these 2 single components on our board. And another big difference in the motor drive, Mappy has these 2 large stepper motors. They're cumbersome and they, from what we saw today, are fairly hard to control. While we have 2 small DC motors that you can't even really see, they're so small, buried in the mouse. So we believe we have a better motor drive as well. And with the shaft encoder feedback, we think we have a better control loop. So we should be able to avoid a lot of the problems that some of the teams are having today, especially with this mouse configuration and its limited sensing capability and no feedback from the motors. USC, we'd be going up an escalator right now.
Hey, here it is. We are at lunchtime.
Hey, Holly.
Forgot the beer, I'm sorry.
Around 250
Double-sided.
Well, we were hoping to run it today, but unfortunately, because of delays in getting the PC board fabricated and all of that, we were unable to go through a software testing phase. So we're not ready to go yet. So I guess by next year's competition.
Yeah.
See the ones that actually run square. We can look ahead for forward walls long before we actually get there and make a decision about
Pass mouse again are the 68HC11 microcontroller. Popular, very popular. It's removed right now to emphasize the fact that we're not functional. Parts of the system that do function, we can read and write to RAM, read from EEPROM. The memory systems are fine. So our address decoding through the mock is fine, as well as the address latch that's programmed in the mock. The laser control is working. There's a laser control register in 373 that allows us to turn them on, go about our business, and once they've charged up completely, there's an interrupt that tells us that they're ready to be read. We read them through the A to D. We can do that. The problem that we're having right now is sending control words in 629 PWM generators.
Specific design process, UCLA, that concentrates on this design.
Exposure to minor relationship. I started with really easy not to find concentrated course. There's an obstacle in the way. What I was talking about, we don't get anymore.
We're hoping to bring our mouse today.
There's Eric, the president of, and Sharon, the treasurer of IEEE.
I'm gonna kill this.
No flash.
Yeah, really. No flash photography.
How was that? That's photo? That's photo? Second try. Confusion range. Better reset it. Bring out his trusty Swiss Army knife.
Tighten the tank.
What school?
Cal State Fullerton.
Ooh.
¿No bailas?